Good afternoon, student. This is the lecture number 13 of unit number 2, that is Introduction to Instrument Characteristics. In this unit, up to previous lecture, we have studied what is characteristics, what is static and dynamic characteristics. Then we have studied different types of static characteristics and different types of dynamic characteristics. Okay, then we have studied first zero order system, first order system and second order system. Okay, today we are going to study what is first order system response, second order system response. Okay, that first order system, second order system is nothing but only the derived form of the zero order, first order and second order system. Okay, a complete solution to the equation describing a dynamical behavior of a system consists of two parts. First one is the complementary function and second one is the particular integral. In complementary function, which refer to the short time or transient response, and particular integral, which refers to the long time or steady state response. A first order system has a transfer operator of the form, that is theta 0 upon theta I equal to k by in bracket tau d plus 1. Suppose we have done the cross multiplication of this equation. In that case we will obtain when the steady state gain or static sensitivity k is unity. Okay, so that k is treated as a 1, then tau d plus 1 multiplied by theta 0 equal to theta I. Okay, a solution to this equation would now be obtained for different standard input. Means what? Solution to that derived relation is obtained for different standard input. Then transient response is nothing but the complementary function. Okay, so this response is obtained from the auxiliary equations, and that is set up by equating the input theta I equal to 0. Now 1 plus tau d into theta 0 comma t equal to 0, that subscript t refer to the transient value. The solution is assumed to be of the form theta 0 comma t equal to a into e raised to mt, where m is an algebraic variable. Okay, or 1 plus tau d into a into e raised to mt equal to 0, that subscript t refer to the transient variable, m is refer to the algebraic variable and t refer to the transient variable. Now after solving we get m equal to minus 1 by tau, and suppose we have put that m equal to minus 1 by tau in the above equation, we will obtain theta 0 comma t equal to a into e raised to mt, and that m is replaced by minus 1 by t tau. That's why a into exponential function e raised to minus t by tau, and the transient response of a first order system is the same for different standard out input. Okay, so that all the relations you have studied in the differential equation by using the generalized variables. Then steady state response for particular integral. The steady state response is given by 1 plus tau d comma theta 0 comma s equal to theta I. That subscript s refers to the steady state value. Subscript s refers to the steady state value. Theta 0 comma s equal to 1 plus tau d in raised to minus 1 into theta I. Theta 0 comma s equal to 1 plus 1 minus tau d plus term in the second differential or and higher order into theta I. Okay, the first step input, the input theta I is a step of constant magnitude, and its differential equal to 0, and therefore we get theta 0 comma s equal to 1 minus tau d theta I equal to theta I. Okay, the total response equal to the sum of the transient response and the steady state response. Therefore, theta 0 equal to a into e raised to minus t by tau plus theta I. At t equal to 0, theta 0 equal to 0. Therefore, 0 equal to a plus theta I equals to, or implies, therefore a equal to minus theta I. Theta 0 equal to minus theta I e raised to minus tau t by tau plus theta I, the transient response and steady state. Okay, therefore theta 0 equal to theta I in bracket 1 minus e raised to minus t by tau, and that is implies to theta I, means here again the cross multiplication is done. Theta 0 by theta I equal to 1 minus e raised to minus t by tau. Okay, so this is the derived relation for transient steady state response. Then the following are the silent features of a first order system. Silent features of the first order system with a step input. Okay, it is the time dependent, its value drop with the time grows, and after sufficiently long time that t implies or t tends to infinity, the value approximate to 0. Thus at theta 0 equal to theta I, that is the magnitude of the output will be same as the input. The magnitude of the output will be same as the input. The time constant tau is the indicative of the speed of response. The time constant tau is the indicative of the speed of response. A large time constant corresponds to a slow system response, and a small time constant represent a fast system response. Thus, in first order system, an attempt should be made to minimize tau for good fidelity, and that fidelity we have studied in case of the uh, dynamic characteristics of the instrument. Okay, at small t equal to tau, then theta 0 by theta I equal to 1 minus e raised to minus 1 equal to 0.632. The vertical difference between the input and response curve is the dynamic error. Okay, so this is nothing but the silent features of the first order system with step input. Then we will have to study the different errors, the classification of errors. In measurement system, the errors could originate from several sources. We know that in the instrument, whatever the static as well as dynamic characteristics we have studied, that may be arises from several sources. So out of that, few sources we have already studied. That is nothing but the inertia of the rotating parts present in the instrument, then wearing and tearing of the instrument, then corrosion of the instrument, environmental condition, uh, how hot and cold the climatic conditions. On that basis, means these are the different sources which could be responsible for the errors, occurrence of the errors in the instrument, and that are broadly classified as follows. First is the gross error, then second one will be the systematic error, and third one will be the random error. Now in second type, that is systematic error, again four types of errors are there: instrumental errors, environmental errors, observational errors, and operational errors. Okay, that systematic errors are occurred by the human negligence. Out of that, the instrumental error or environmental, observation and operational errors are because of the human negligence or operators negligence. Okay, in that, the gross error, first type of error is gross error. These errors occur due to the human mistake in reading instrument and recording and calculating result of the measurement. Means while measuring the reading, whatever the mistake done by the human or operator, that is nothing but the reading instrument recording and calculating results of measurement. Okay, means he if he shows his negligence while measurement, in that case, means in case of recording and calculating the result. Okay, so there may be a chances of occurrence of the gross error, although it is probably impossible to eliminate the gross error completely. Means generally it is impossible to eliminate the gross error completely, because uh, human interference is there for the measurement, and that's why we cannot eliminate completely these gross errors. Okay, yet one should try to anticipate uh, and correct them, but um, everyone can minimize them. Okay, or what we can say, that anticipate and correct them. The mathematical analysis of a gross error is impossible, since these may occur in different amounts, and analysis of these errors are also, mathematical analysis is impossible because they may be occur in different amount. Okay, while some gross errors may be easily detected, others may uh, unnoticed. Okay, means as there are some type of gross errors are noticeable, they can be detected easily, and some are unnoticeable, means they cannot be observed. Okay, so that cannot be eliminated completely. So these errors can be avoided by adopting two means. Means that gross errors are mm, avoided by adopting two means, in that the immense care should be taken while taking the reading and recording the data. Means very much care to be taken for taking the reading and recording the data. Means suppose we have to take the immense care for the measurement of and reading and recording of the data, then 2 3 or even more readings should be taken for a quantity being measured. Okay, for the same quantity we will have to take the 2 3 or even more reading for the single measurement or single entity measurement, so that we can compare the uh, reading and measurement comparatively with each and every measurement. Okay, so designers of instrument to some extent can take care to avoid gross error. Okay, designers designers of instrument to some extent can take care to avoid gross error, but much would depend upon the interest and competence of the observer. Yes, whatever the designers of the instrument, they take care up to some extent to avoid the gross error, but much would depend upon the observer, or what we can say, that the operator, how to minimize that gross error. Designers of the instrument, okay, the designers of the instrument to some extent can take care to avoid the gross error, but much okay, that we have repetition of the last point. Then next is the systematic errors. These errors are repeated consistently with the repetition of the experiment and are caused by such factors. So such some systematic errors are uh, caused because of the repetition of the experiment and are classified as uh, systematic or sensitivity shift, zero offset, and known non-linearity. These are the reasons or causes, what we call it as a causes of the systematic errors. These errors cannot be determined by direct or repetitive observations. Means that gross errors can be observed by uh, direct and repetitive observations of the measurement made each time with some technique. These errors can be located only by having repeated measurement. So these type of errors can be located only by having repeated measurement under different condition or with different equipment, and where possible by an entirely different methods. Okay, so these errors may be instrumental, environmental, or observational errors. Means whatever the systematic errors are, instrumental errors, environmental errors, or observational errors. Okay, so this is nothing but the systematic error. Then random errors are accidental, small, and independent. Whatever the random errors are accidental, small, and independent, they vary in an unpredictable manner. Okay, so there is no any kind of prediction we can do for the occurrence of the error. So these type of errors are random errors, and these type of errors occur accidentally. It may be small and independent. There will be no dependence one or other parameter. Okay, the magnitude and the direction of these errors cannot be predicted from knowledge of measurement system. However, these errors are assumed to be follow to law of probabilities. Okay, so the magnitude and direction of these errors cannot be predicted from the knowledge of measurement system. Means, as one will say, I have experienced one, or suppose any operator will say, I have experience of so much, I have so much experience for the measurement, but the magnitude and direction of this error cannot be predicted from the knowledge of measurement system. Okay, and these errors are assumed to be followed to the low law of probabilities, and that errors follow the law of probabilities. The most common causes of these errors are friction in instrument movement, backlash in the movement, parallax errors between the pointer and the scale. Now, what is that parallax? If there is a um, analog instrument means the instrument is having the display pointer over the calibrated scale. Okay, so for the protection, the glass is provided over that measuring devices. Okay, so as we are observing the pointer from the top of the that, or what we can say, exactly from the front side of that measuring device. So what will we will observe that what we can say, that pointer of the measuring device is exactly overlapping the marking of the calibrated scale. But suppose we are observing that scale or the pointer of the instrument from somewhat offset. Okay, in that case we will or it may be appears to be intersecting with the other marking from the measured one. Okay, so that is nothing but the parallax. Are you getting it? समझो अपन जो भी ग्लास है या फिर पॉइंटर उसके एग्जैक्टली परपेंडिकुलर पॉइंट ऑफ व्यू से अगर देख रहे हैं, तो वो जो पॉइंटर है वो क्या एग्जैक्टली मैच करते हुए दिखेगा कुछ पर्टिकुलर रीडिंग के ऊपर और मार्किंग के ऊपर, कैलिब्रेटेड मार्किंग। अगर वही अपन थोड़ा दूसरे एंड से या फिर साइड से देखेंगे, तो सेम पॉइंटर वी कैन फाइंड appears to be intersecting with the other marking of the calibrated scale. So in that case we must have to take the precaution to always measure the what we can say that reading from the top of the measuring scale. so that we can avoid the parallax error. Okay, that backlash error is the back end of the instrument. Then finite dimensions of the pointer and scale divisions. Then hysteresis in elastic members that we have studied in the dynamic characteristics. Then mechanical vibrations, and that mechanical vibrations occur because of what? Mechanical vibrations are occur because of the inertia of the rotating component present in the instrument, such as a gear, pulley, then mountings, different mountings. Because of that, the mechanical vibration noise will occur. Okay, wear and tear of the component will occur, and because of that, the random errors occur. Then uh, finite dimensions of a pointer and scale deviation, uh, as there is no calibrated scale, or the calibration of the instrument is not done from last from longer period. In that case, there may be a chances of occurrence of giving the reading which is not accurate. Okay, so the friction in the instrument movement, so the moving parts are there. In that case, there will be friction between the matting parts, and because of that also the random errors occur. Okay, the next one will be the backlash in the movement. Backlash in the movement is what? It is nothing but uh, in the back end of the instrument there will be a chances of occurrence of some errors, and that is nothing but the error caused by the random errors. Okay, so in today's lecture we have studied the classification of errors, in that gross error, systematic errors, and random errors. Okay, so in the next lecture we will study the sources of errors. What are the different sources of errors? uh, okay, so that we will cover in the next lecture, or we will complete here itself. Beside the errors so far discussed, out of the physical and mechanical nature, the errors which necessarily result from the faulty calibration of measuring system, and the error arises from the following sources also: the response time, design limitation, energy exchange by interchanging. Okay, so these are the different errors. Then transmission, deterioration of the measuring instrument, ambient influence on measuring system, errors of observation and interpretation. So these are the different sources of error, and which cannot be, or which can be eliminated. The response time, design limitations, what are the different limitations to be imposed while designing the instrument. Then energy exchange by interchanging, or what we can say that interactions. So noise, it is defined as any signal that does not convey useful information. Noise means what? It is defined as any signal that does not convey useful information. Noise signals error can be reduced to a minimum level through filtering. Noise signals can be reduced to a minimum level through filtering, careful selection of component, shielding and isolation of the entire measurement system. So this is nothing but the sources of error. In the upcoming lecture, we will conduct one multi-choice question test on this second unit. Okay, and same way I will share the notes of the second unit, PDF notes of the second unit on your WhatsApp group. You just go on through it and try to solve the MCQ based test. Okay, so today we will stop over here, and whatever the doubts you have in today's lecture we will discuss in the Google Meet. So